Maximum power point tracking, or sometimes just power point tracking, is a technique used commonly with wind turbines and photovoltaic solar systems to maximize power extraction under all conditions. Although it primarily applies to solar power, the principle applies generally to sources with variable power, for example, optical power transmission and thermophotovoltaics. PV solar systems exist in many different configurations with regard to their relationship to inverter systems, external grids, battery banks, or other electrical loads. Regardless of the ultimate destination of the solar power, though, the central problem addressed by MPPT is that the efficiency of power transfer from the solar cell depends on both the amount of sunlight falling on the solar panels and the electrical characteristics of the load. As the amount of sunlight varies, the load characteristic that gives the highest power transfer efficiency changes, so that the efficiency of the system is optimized when the load characteristic changes to keep the power transfer at highest efficiency. This load characteristic is called the maximum power point, and MPPT is the process of finding this point and keeping the load characteristic there. Electrical circuits can be designed to present arbitrary loads to the photovoltaic cells and then convert the voltage, current, or frequency to suit other devices or systems, and MPPT solves the problem of choosing the best load to be presented to the cells in order to get the most usable power out. Solar cells have a complex relationship between temperature and total resistance that produces a nonlinear output efficiency which can be analyzed based on the IV curve. It is the purpose of the MPPT system to sample the output of the PV cells and apply the proper resistance to obtain maximum power for any given environmental conditions. MPPT devices are typically integrated into an electric power converter system that provides voltage or current conversion, filtering, and regulation for driving various loads, including power grids, batteries, or motors. Solar inverters convert the DC power to AC power and may incorporate MPPT. Such inverters sample the output power from the solar modules and apply the proper resistance so as to obtain maximum power. The power at the MPP is the product of the MPP voltage and MPP current. Photovoltaic cells have a complex relationship between their operating environment and the maximum power they can produce. The fill factor, abbreviated FF, is a parameter which characterizes the nonlinear electrical behavior of the solar cell. Fill factor is defined as the ratio of the maximum power from the solar cell to the product of open circuit voltage VOC and short circuit current ISC. In tabulated data, it is often used to estimate the maximum power that a cell can provide with an optimal load under given conditions, P equals FF VOC ISC. For most purposes, FF, VOC, and ISC are enough information to give a useful approximate model of the electrical behavior of a photovoltaic cell under typical conditions. For any given set of operational conditions, cells have a single operating point where the values of the current and voltage of the cell result in a maximum power output. These values correspond to a particular load resistance, which is equal to V/I as specified by Ohm's law. The power P is given by P equals V*I. A photovoltaic cell, for the majority of its useful curve, acts as a constant current source. However, at a photovoltaic cell's MPP region, its curve has an approximately inverse exponential relationship between current and voltage. From basic circuit theory, the power delivered from or to a device is optimized where the derivative d/dV of the IV curve is equal and opposite the I/V ratio. This is known as the maximum power point and corresponds to the knee of the curve. A load with resistance R equals V/I equal to the reciprocal of this value draws the maximum power from the device. This is sometimes called the characteristic resistance of the cell. This is a dynamic quantity which changes depending on the level of illumination, as well as other factors such as temperature and the age of the cell. If the resistance is lower or higher than this value, the power drawn will be less than the maximum available, and thus the cell will not be used as efficiently as it could be. Maximum power point trackers utilize different types of control circuit or logic to search for this point and thus to allow the converter circuit to extract the maximum power available from a cell. If a full power voltage curve is available, then the maximum power point can be obtained using a bisection method. When a load is directly connected to the solar panel, the operating point of the panel will rarely be at peak power. The impedance seen by the panel determines the operating point of the solar panel. Thus, by varying the impedance seen by the panel, the operating point can be moved towards peak power.